Okay, in this video we're looking at two things: the inverse of a function and composition of functions. And the second one you might have seen a bit of before, hence the phrase composite functions. Okay, so the composite of function is a function of a function, and it's often denoted like that. Notice the dot that's not filled. And f of g might be one way of saying that, or f of g of x. And it can be written also like that. So it can be just like that, or like either of those two there. They all mean the same thing. You need to be fluent with all types of symbols. So we're talking about a function of a function, composite function, or composition of functions, the process. So if we're looking at this function notation here, f of g of x, the composite function, the range of g must be within the domain of f. Okay, so let's have a look at all of this in action. And if we're given an example here, we've got f of x equals x squared minus 2, g of x equals 3x minus 5. Calculate f of g of x. So if f of x is x squared minus 2, f of g of x would be, wherever we see x, we're going to sub in the other function. So instead of x squared, we would have 3x minus 5 all squared, and then minus 2. And because that's a perfect square, we've got 9x squared. Okay, so it's ax squared minus 2ab plus b squared, as you know. So that's minus 30x, and that's plus 25. And then we have to subtract the 2 off. 9x squared minus 30x plus 23 is our answer there. Part B, f of g of 3. That simply means for the f of g of x that we just found, we need to substitute the value of 3 in. So f of g of 3, if we write it down as given there, would be 9 times 3 squared minus 30 by 3. That's a 30 times 3, 23, and that comes out as 14. Now for part C, we've got g of f of x, which is different, and basically wherever we've got the x and the g of x, we're going to replace that with this other function f of x. So g of f of x equals, so we've got 3 times x squared minus 2 in place of the original x, and then minus 5. So we have 3 times, let me remove those brackets, 3 times x squared, so distributive rule, minus 6 minus 5, and that's 3x squared minus 11. Finally, it's simply just a matter of subbing in 3 for this one here, and you'd have 3 by 9, which is 27, take 11, which is 16. Now we move on to phase 2, which is inverse functions. Or if it's not a function, only a relation, it's an inverse relation, which is going back to what you've studied before, relations versus functions. One way of determining a function is the vertical line test. Just a reminder there, if a relation has a symbol m, then the inverse would be denoted as m inverse as such. Okay, and just seeing in terms of ordered pairs and mappings, so if we're given m is this mapping here, the inverse changes the direction, so it's heading from right to left in all cases, and so ordered pairs are switched around. So if we had 3, 7, we would then have 7, 3, and and as you can see, the ordered pairs are switched around, and that corresponds with the mappings switching around. So that's essentially how we look at inverse. We'll have a closer look at this in a future video, but two functions are inverses if they're symmetrical about the line y equals x. Just another little feature there, which we'll get into a bit more in another video. In an example here, we've got a relation which is a function as well here. Find if f of x equals 5x minus 8. This here means find the inverse function of f of x. So in part A, if we've got f of x is 5x minus 8, we need to go through the process of finding the inverse, which is as follows. Step 1 is to make x the subject. Okay, so what we can do in order to facilitate that is change our notation from the function notation and instead use y for the given function. So we need to make x the subject. So you should have the algebraic skills by now to do this. Oh!
Sorry.
Hold on. Sorry, just had a knock at the door then. The next couple of lines there are set. Now, we need to look at this. In function notation, we've got now the inverse function, and that's written. So it's the inverse function of y, isn't it? Okay, so the inverse function of y is y plus 8. So therefore, it's customary to write the dependent variable and the independent variable in the following way. So I would write new function is this. We've just created a new function. In order to plot it with a graphics, one way of thinking that, in order to plot this in a graphics calculator, you'd need to enter that in, wouldn't you? Okay. Oh, and sorry, when I got the knock on the door, I was just about to write a divide by 5 there. Apologies. So that's over 5, and that's over 5. You might have been wondering, why didn't you divide by 5? And you're right, I meant to. And divide by 5. Okay. So knocks at doors, you lose your train of thought, and there we go. So you understand that this is the inverse function here in terms of the original variables, but in order to plot it on a graphics calculator or plot it on Cartesian axes, this is one of the reasons why we switch the variables around. Now if we plot those two, they will be symmetrical about y equals x. Okay, which I've just done here, and you can see that we've got y equals x in the middle and the others are symmetrical about it. Okay, so, and you can perhaps now see why we've got to switch the variables around in order to get the function. For the following here, inverse f of 4, and this will be the final one on this video, and we've got inverse f of 4. We've got to interpret that first of all. In our function inverse f of x, we've got to substitute the value of f of 4. Now the value of f of 4, so let's do that first. F of 4 would be 5 times 4 minus 8 minus 8 from what we're given there, which is 20 minus 8, which is 12. So now we can sub that in, and we've got this, and we sub in 12 in here. So we've got 12 plus 8 over 5, which is 20 over 5, which is 4. One for you to try, the final one here, f of inverse f of 22. So try that. It's different to that one, but it's the same concept, and you should get 22 as your answer if you've understood the video, because